This is part 2 of the presentation on shallow neural networks. Multi-layer neural networks. These networks, as the name suggests, use multiple layers of neurons to achieve desired learning. These networks are constructed using smooth activation functions, for example, sigmoidal or ReLU function. And these networks can have many hidden layers, although I have shown only one hidden layer, but one can have multiple hidden layers. These networks are also known as MLP, which stands for Multiple Layer Perceptrons Networks, as well as BP networks, which stands for Backpropagation Network. These networks are capable of generating arbitrarily complex models. The learning in these networks is done via error minimization, and this learning technique is known as backpropagation learning. A typical behavior of this learning is that it takes long training time, as well as the performance or the results of learning are affected by the size of the network. How do we train a multi-layer neural networks? Basically, we follow supervised learning. We are given a collection of vector pairs, x sub I and y sub I. Every vector x is a vector of real numbers of some suitable dimensionality, maybe 10, 20, 50, depending on the problem. Every vector y could be every yi is a vector with components either 0 or 1 when we are using sigmoidal activation function, or -1 or 1 when hyperbolic tangent function is used. When the network has a single output, then of course yi's are all scalar quantities. To train the network, we set up a loss function at the output and use gradient descent to adjust the weights at the output layer to minimize the loss function. And then the gradient at the output is fed back to internal layers to adjust their weights. And this feeding back is based on chain rule of differentiation. And the resulting algorithm is known as the backpropagation algorithm, because we are kind of propagating back towards the input side the error from the output. Let's look at the chain rule, which you must have done way back. So let's say that we have a function f of y, and this function is sine of y. And let's say that y further is a function gx of another variable x, and gx is given as 0.5 x squared. So if you were to calculate df by dx, that is how much f varies when x is varies, or how f is influenced by x, then df by dx can be calculated as df by dy times dy by dx. And for the given expressions for f and g, this turns out to be cosine 0.5 x squared times x. Let's look at another example of chain rule here. In this case, let's say on the leftmost figure, there is an output z, which basically is being driven by two variables y1 and y2. And y1 and y2 in turn are being driven by three variables x1, x2, and x3. So if one was to calculate how z is going to depend on x1, that is to calculate dz by dx1, we can calculate that as dz by dy1 times dy1 times dx1. That is the red line or the path shown over here. But z is also dependent on is also controlled by y2, and y2 in turn is dependent on x1 over here. So there will be a second term here, and that will be dz by dy2 times dy2 by dx1. And similarly, you get the expressions for dz by dx2 and dz by dx3 for these two figures. So essentially, chain rule is exploiting dependencies between different variables. And chain rule is the one that is used to figure out how the output is dependent on the intermediate weights and so on. So the training of a backpropagation network, or MLP training, works in two phases. There is a feedforward phase and there is a backpropagation phase. Feedforward phase is the one where you put the input to the system, and this input is propagated in the forward direction all the way to the output to figure out what output is being produced for that given input and given set of weights at that particular instant. And that output then is compared with whatever is desired. You get an idea of error, and then that error is propagated back to figure out how to adjust different weights. So that is known as the backpropagation phase. And of course, once a network has been trained and put in practice, or you are testing its performance, the only phase that comes into play at that time is the feedforward phase, because you are not making any adjustments to the weights at that time, so there is no need for any backpropagation phase at that time. Now, instead of showing you the derivation of the backpropagation algorithm, what I'm going to do is I'm going to show you an example, and in that example I'll just show you how to calculate changes for two weights, and that will give you an idea of how backpropagation works. If you want to look at the complete example, here is the link for the example, so you can go and take a look at it. The example consists of a feedforward network as shown here. So network has two hidden neurons in a single hidden layer, and it has two output neurons, O1 and O2, and there are three inputs, X1, X2, and X3 to the network. The different weights are all shown in the picture, and let us assume that the input to the network is X1 equal to 1, X2 is equal to 4, X3 equal to 5. And let us say for output unit O1, the desired or the target output that we want is 0.1, and for unit O2, the target output we want is 0.05. So let us say that with this, let's try to figure out how the weights will be changed for the given input of X1 equal to 1, X2 equal to 4, X3 equal to 5. So first let us do the forward propagation. So let us move from input to the hidden layer and then from the hidden layer to the output layer. So let us call the net sum for the first hidden layer neuron as ZH1, and that net sum will be given by W1X1 plus W3X2 plus W5X3 plus B1. And similarly, the net sum for the second hidden neuron, let us designate it as ZH2, and this will be given by W2X1 plus W4X2 plus W6X3 plus B1. This is based on the configuration of the network that we have. Now, this net sum is going to be fed to the activation function. So let us say H1 is the output of the activation function for the hidden layer neuron 1, and H2 is the output for the hidden layer neuron number 2. And from the hidden layer to the output layer, the relationships are, that is the output layer neuron number 1, the net sum for that neuron will be given by W7H1 plus W9H2 plus B2. And for the second output neuron, the net sum designated as ZO2 will be W8H1 plus W10H2 plus B2. And again, sigmoidal functions are there, so the output O1 will be sigma ZO O1 and O2 will be sigma Z O2. Now if you plug in all the numeric values that are shown in the picture on the previous slide, you will find that the net sum for the neuron number 1 in the hidden layer is 4.3, and the output after feeding through the sigmoidal is 0.9866. Similarly, the net sum for the second neuron in the hidden unit is 5.3, and activation output after the sigmoidal function is 0.9950. On the output side, the net sums are 2.08 and 1.388 respectively, and the O1 is 0.8896 and O2 is 0.8004. So these are numbers you will get just by plugging in the numeric values that are given. Now let's look at the backpropagation calculations. And just to show you, first let us look at how this weight is affecting the output. So let's say that the error we are defining here is 1 by 2 O1 minus T1. O1 is the output we are getting. T1 is the target output we want from that neuron. Square plus O2 minus T2 square. So if you take the derivative of E with respect to O1, that turns out to be O1 minus T1. Similarly, dE by dO2 turns out to be O2 minus T2. And if you want to calculate dE by dW7, that is through chain rule is given by this expression. Each term here can be calculated. So if you look at dE by dW7, you will find that this turns out to be O1 minus T1 times O1 times 1 minus O1 multiplied with H1. This is nothing but the delta of generalized delta rule, if you remember. So that's really what it is. And once you plug in the numbers, you will find that dE by dW7 is 0.0765. So this part of the weight change that is in the output layer is pretty similar to what we have seen earlier for the sigmoidal neuron. Let's look at weight W2. This is the weight W2 here. And let us see how error is dependent upon this particular weight. So let's look at dE by dW2. So you will find that dE by dW2 through chain rule can be expressed as dE by dH2 times dH2 by dZH2 times dZH2 by dW2. So basically this weight here is affecting output O1 through H2. It is affecting output O2 through H2. So those terms need to be incorporated in our expression. So if we look at dE by dH2, that is taking care of outputs at O1 and O2. So those are the two terms you get there. And once you write down this, each individual term you can see can be easily obtained, the numeric value there. So dE by dH2 then turns out to be this expression, which evaluates to 0.0818. So if we plug in this value into our formula over here, basically dE by dW2 turns out to be 0.0004. So that tells us how that weight needs to be, how much that weight needs to be changed. And similar calculations can be performed for rest of the weights. So that's basically what backpropagation does, or how weights are calculated in backpropagation. You can go and look at that link, and in that link you will find that they have done the calculations for each and every weight. So that way you will get a full picture of how each and every weight is changing. So based on this, one can summarize the backpropagation algorithm as follows. All weights are randomly initialized, and we go over the forward and the backward passes using the training set, adjusting the weights. During every pass, the training data is typically shuffled so that you don't present the same sequence of examples to the network. And the training stops when error reaches an acceptable level. Now, there are a number of practical issues that are involved in backpropagation training, and people have found that if you don't take care of these issues, generally the training will not be that good, or it will be very, very complicated and very long. So let's look at some of the important issues that are involved in doing the backpropagation training. So number one is what people have found is that normalization of the data helps avoiding dominance by a subset of input features. For example, if some features have very high value and some features have very low value, chances are the features with high value will tend to dominate the calculations. And that will not help moving towards the minimum goal in an easy fashion. So generally what people like to do is to normalize the data. So as an example here, you can see in the leftmost panel is a distribution of data in 2 dimensions. To do the normalization, first thing you do is you basically zero center the data. That is, you calculate the mean of the data vector or mean vector and ensure that the mean vector sits at the origin of your feature space. So in this case, it's 2-dimensional data, so mean should be sitting at the origin of the 2-dimensional coordinate system. And once the mean has been done, then we normalize the data so that it has unit variance. That way, basically, we ensure that there is no particular component of the data that is going to be dominating. So this normalization is important and generally preferred and is performed right at the beginning. Another point is, when do we stop the training? As I said, the training can be long, so one needs to figure out when we have reached a stage where it's good to stop the training. And to do that, typically what people do is they take the total available data that you have for building your model, and you divide that data into 3 parts: training set, validation set, and test set. Training set obviously is used for training, and it turns out that if you keep on training and keep on going through iterations, you will keep on decreasing the error. But that kind of training can lead to what we typically call as overfitting. So generally what people do is they will say, all right, let us train it for certain number of iterations, bring in the validation set, and see what is the performance on the validation set. Train some more, bring back the validation set, see the performance. Continue doing that. So at some point you will find that initially the validation set is giving you poor results, but at some point somewhere here, the validation set starts showing improved performance. So wherever you get that knee point or a break point, that is the point where you kind of stop training. So typically you will use the validation set to figure out when to stop training, and then once the model has been constructed and training has been stopped, you can use another independent set which is known as the test set, and you can then figure out how is your model performing on that test set. The weights in the network are initialized, so people have found that if you don't initialize them in a proper fashion, again, the network may not converge, or it may take very, very long time to converge. So it's a good practice to choose hidden unit weights in the range of -1 divided by square root of d to 1 square divided by square root of d, where d is the dimensionality of the input vectors. Through empirical means, people have found that if you set the weights like this, initialize them like that, you end up getting pretty good training and pretty reasonable in a reasonable amount of time. And for the output units, again, the range has been figured out through empirical means, and that is shown as in this slide. So the above choices for initialization ensure that all units learn at the same pace, and learning typically will begin from a state where each unit is operating in the linear part of its activation function. So that way every unit has a good chance to learn. Now, nowadays, there are packages that you will be using rather than writing your own code for backpropagation. So these packages do ensure many of these issues when they are initializing the weights and figuring out things like that. Number of hidden units, of course, is to be determined by you when you are building a model. And what people have seen is that if you are using fewer hidden units, you end up with relatively simpler decision boundaries. If you have many more hidden units, you will end up with complex boundaries. Now, the number of hidden units also kind of places a requirement in terms of training data, because if you have very large number of hidden units, then correspondingly you should have a reasonably large number of training examples, so that there is a good match between the training data size and the number of unknown parameters or weight values that you need to calculate. So a popular rule of thumb is to choose the number of hidden units such that there are roughly 10 training examples per weight. This is again a rule of thumb that you can use to figure out how many hidden units you should have. Sometimes people like to use what they call as the momentum term, and this momentum term kind of speeds up the training. And the basic idea of momentum term is simply to add an additional component to the weight change expression, and this additional component reflects the previous weight update. If the previous update was slow, this component will have a small value. If the previous update was large, then this component will have a large value. And again, people have found that by adding the momentum, the training can be made faster. Another issue in running backpropagation is learning rate. Learning rate is typically not kept fixed, but changed as per one of the following three schedules. One is step decay, that is, you reduce the learning rate by some factor after every few epochs. Typical values might be reducing the learning rate by a half every 5 epochs, or by 0.1 every 20 epochs, or whatever you want. Exponential decay, in this case, we use a formula to figure out how the learning rate should be falling down. Or 1 by t decay, where basically as the time goes on or as the number of iteration goes up, the learning rate keeps going down by a formula that is shown here, alpha equal to alpha 0 divided by 1 plus k times t, where alpha 0 and k are some suitable constants or parameters. All the parameters involved in training a multi-layer neural network are typically called hyperparameters. And everybody knows that the choice of these parameters is quite crucial or important in getting good accuracy, as well as in terms of making the system learn at a reasonable pace. Another one is, of course, whether we should be using batch training or SGD or mini batches. And of course, nowadays SGD really stands for mini batches. So typically SGD is what on mini batches is what we use. And of course, there is a shuffling of examples done at every epoch. That shuffling is important so that the network doesn't see the same pattern of input examples all the time. So what we are going to do now is to give you some illustration of MLP training. And in the following slides, the results of different training configurations will be shown. And these configurations involve different activation functions, different number of hidden layers, etc. So that way you will get an idea of how the learning is related with choice of some of these parameters. So let's start with a very simple example. We have a two-dimensional synthetic data that is shown here in the figure, and using this data we basically split it up into training and test sets, and we basically then train a network with a different number of hidden layers and see how the results turn out to be. The idea of random state is equal to 42 that I have set here is to ensure that every time you run this program, you will get the identical initialization, because the results do depend on initialization. So if you want to compare the performance by changing some parameters, you want to make sure that you do the identical initialization every time. And by specifying a random state, we ensure that the results are reproducible every time you run it. So in this case, we use the logistic activation, which is same as the sigmoidal activation. And the solver here refers to the particular optimization method that has been used. And of course, in this case, the results are being obtained using the sklearn library. All right. So in this case, with the sigmoidal function and specified solver, we are able to get training accuracy of 81% and test accuracy of 60%. Obviously, this is not a linear problem, so that's why we are getting results that we are getting. If we change the number of some parameters, in this case, then training accuracy falls to 81 and test accuracy falls to 60 degrees. So that is what we are showing here. So what I did is I ran this example with different parameters. So some of those results are shown here. So hidden layer size is 2. That is, we have 2 neurons. The learning rate is 0.05. Activation function is logistic. Training accuracy is 80%. Test accuracy is 60%. And these results are not much different from hidden layer with 5 neurons. So there is not a big difference. That was 81 and 61% or something like that. And now we are getting 80 and 60%. Let's look at another set of results. So in this case, the hidden layer size has been increased to 10. The learning rate is kept same. Activation function is logistic as it was used earlier. Now the training accuracy has gone up from 81 to 95. That's because we have many more hidden layer neurons now. But at the same time, the test accuracy has gone down 45%. So you can see here the accuracy for training data is gone up, because what is happening is that with 10 hidden neurons, the network is trying to copy or mimic the input examples that you have. And also, because of that copying, you see that the boundary that we are getting is fairly complex, which means in this case there is a lot of overfitting that is going on, and that's why on test data the accuracy is low, but on the training data the accuracy is very high. Let's keep the hidden layer size 5, but let's change the activation function from sigmoidal to hyperbolic tangent. So if we do that, basically training accuracy becomes 84% and test accuracy is 75%. So if we compare this result with the result that we got with sigmoidal activation with 5 hidden units, you can see that hyperbolic tangent is giving slightly better performance or slightly better results. Let's change the hidden layer to 2, keep everything else same. Again, with training accuracy 81%, test accuracy 70%. Looking at the boundary, we see results are good. There is no hint of overfitting. With hyperbolic tangent, let us increase the number of hidden units to 10. So again, you find that training accuracy has gone up to 85, test accuracy is 80%, but the boundary is fairly complex. So there is an overfitting going on, but not as much as it went on with the sigmoidal function with 10 hidden neurons. So some of these examples or results should give you an idea of what happens when we change the number of hidden units and when we change the activation function, etc. This example shows you the effect of normalization. So in this case, the problem that we are addressing is wine data. There is a wine data set that's out there in the public domain that a lot of people use to demonstrate different algorithms. So we are using that wine data to basically train a feed-forward network to do the classification prediction. So without normalizing the wine data, the accuracy on the training set is 92% and the test accuracy is 81%. On the other hand, if we keep everything else same but normalize the training data and then do the training, we find that training accuracy jumps up to 100% and test accuracy jumps up to 98%. So that shows you very clearly that if you don't perform normalization, there will be certain attributes that will be dominating the calculations, and because of that dominance you may not get really good results. So what you want to do is you want to ensure that every time you use MLP or feed-forward neural networks, you perform the normalization on the input data. One thing we had mentioned earlier is the idea of regularization. So when you have many hidden units and if you want to control the overfitting, what you can do is you can introduce a regularization term in your cost function. So here is an example of what happens when you introduce a regularization term. So in the leftmost panel, the regularization term has been included, but the weight that we are giving to that term is given by value of lambda, which is basically 0.001. That means really very, very small weight is being given to the regularization, effectively no regularization. So if we use 20 hidden neurons for a given problem on which this data has been trained, basically the boundary looks very complex, as you can see in the leftmost panel. Come to the center panel. In this case, the regularization term has a parameter value of lambda equal to 0.01. That means it's a reasonable value. And because of that, the boundary that we are getting now is much, much smoother, and the performance of this boundary is not that different from the boundary that we got in the left hand panel. In the rightmost panel, the lambda value has been increased to 0.1. So in this case, the boundary is almost becoming linear. That means too much regularization is being done. We are drastically controlling all the weight values and kind of not allowing the network to learn as much as it could learn. So again, the idea of using regularization is good, but at the same time, the proper choice for how much weight to be given to regularization is an important thing that needs to be considered carefully. Another practical issue in running backpropagation is dropout. The idea of dropout is that some neurons selected at random at each training step do not participate in producing the output and getting their weights updated. So what we are saying here is that at random, let's pick some neurons in the hidden units and let those neurons not send their output to the output units. And the hidden unit neurons that are picked at different times are picked randomly. So effectively what people have demonstrated is that by doing this dropout idea, we are effectively doing something equivalent to regularization. And this mechanism kind of avoids overfitting in a manner similar to what regularization done. So sometimes people prefer doing dropout rather than doing regularization. So at this point, we have covered all the basics of multiple layer feed-forward networks. So question is, what is next? So as we have seen, the feed-forward or multilayer neural networks operate upon data representing feature vectors. And these networks are used either as classifiers or regressors. Although we have mostly talked about classification, but basically you can use these networks for regression problems as well. Now, by adding layers to these networks at the front and making such layers capable of learning features, we can create networks that are capable of learning features as well as classification. And such networks are basically what deep learning neural networks are. And that is what we are going to be talking next. Thank you.